Hey everyone, and welcome. Have you ever wondered what language your computer actually speaks? Today, we're going to peel back the layers of software and get right down to the metal. We're talking about assembly language, the computer's true native tongue.
Okay, so take a look at this on your screen. BARP again. I mean, what is that, right? It probably looks like total gibberish, but stick with me, because by the end of this, you're going to know exactly what this little piece of code is telling the computer to do. So, any guesses what it means?
Well, it all starts with understanding what assembly language even is. You can think of it as the ultimate Rosetta Stone for computers. It's that crucial link, that translator that takes all the high-level code we write, Python, Java, whatever, and turns it into the raw binary, the ones and zeros, that the processor can actually understand and act on. So just like learning any new language, you've got to start with the basic sentence structure, right? And that's exactly what we're going to do here. We're going to break down the anatomy of a single line, a single instruction of assembly code. And here it is, the basic format. This image breaks it down perfectly. You'll see that pretty much every single line of assembly you ever see will follow this four-part pattern. You've got the label, the opcode, the operands, and comments. And you'll notice some are optional, some are required, and that's a really important distinction we're going to keep in mind. All right, first up, we've got the label. Now, this part's optional. The best way to think of it is like putting a bookmark in a book. You're just giving a specific line of code a name, something memorable, like loop start or pay again. Why? So you can tell the computer, hey, jump back to this exact spot later. It is super useful for things like loops. Next, we have the opcode. Now, this is the absolute heart of the instruction. This is the verb. It's the action word. It's the part that tells the computer what to do. Should it add two numbers? Should it load some data from memory? Or maybe branch to a totally different part of the program? The opcode is the command. But, a verb doesn't do much without a noun, right? And that's where the operands come in. They're the subjects of our little sentence. If the opcode is add, the operands are the things you're telling the computer to add. They point to the data, or the registers, or the memory locations where that action is going to happen. And last but not least, we have comments. See that semicolon? Anything that comes after it is completely 100% ignored by the computer. This part is just for us, for the humans. It's where you leave notes for yourself or for other programmers to explain why you're doing what you're doing. And let me tell you, good comments are absolutely crucial for writing code that anyone can understand later.
Okay, so we've got the sentence structure down. Now let's build up our vocabulary. What are the common words and, the grammar rules that let us actually write something useful in assembly?
Let's look at a few of the big ones. Here are some really common opcodes, those verbs we were talking about. You've got simple stuff like add for, addition. LD is for load, which just means grabbing some data from memory. And then you have these cool conditional commands like BRP. That stands for branch of positive. It's like telling the computer, hey, if the last thing you did resulted in a positive number, then I want you to jump to this other spot in the code. So what are these opcodes actually working with? What are the operands? Well, they usually come in three flavors. They can be registers. Think of these as little lightning-fast scratch pads right on the CPU itself for quick calculations. They can be immediate values, which is just a fancy way of saying a specific number, like 5, or they can be those labels we just talked about, pointing to a memory address.
Okay, here's a really important point. Not every line you write is an instruction for the CPU. Some lines are what we call directives. These aren't commands for the processor, they're instructions for the assembler, the program that's translating our code. You can think of them as setup instructions. They don't make the CPU do anything, but they tell the assembler how to build and organize the final program.
All right, enough theory. Theory's great, but let's see this stuff in action. We're going to walk through a real simple program to see how all these pieces fit together. What are we going to do? We're going to multiply a number by 6. Simple, right?
Okay, first things first, we have to set the stage. That ORIG directive, that's just telling the computer where in memory to put our program. Then we use LD, or load, to get our data ready. We load the number 6 into a register, R1, which is going to be our counter. Then we load whatever number we want to multiply into another register, R2. And finally, we just clear out a third register, R3, to make sure it's empty and ready to hold our final answer.
And now for the main event, the loop itself. See that label there? Again, that's our bookmark. The first line adds our number from R2 into our result register, R3. The next line subtracts 1 from our counter in R1. And here is the magic. That BRP again instruction checks if the counter is still positive. If it is, boom, the program jumps right back up to that again label and does the whole thing over. And it's just going to keep doing that, adding and subtracting until the counter hits 0.
So once our counter finally hits 0,
that branch if positive condition isn't true anymore. The program doesn't jump. It just falls through to the next line. And what's that? Halt. Program over. The processor stops, and those last two lines, they aren't even instructions. They're just directives telling the assembler, hey, set aside a spot in memory for our number, and, oh yeah, put the value 6 in memory and call it 6 for me.
So there you go, a complete working program. But there's a catch. Right now, it's just a text file. The CPU has no idea what to do with this. It can't read add or LD. So what's that final, absolutely critical step that turns our nice, human-readable code into the ones and zeros the hardware actually speaks?
The magic is all in something called a two-pass assembler. It's a two-step process. On the first pass, the assembler zips through your code, but it doesn't translate anything. It just looks for all your labels, like again and 6, and builds a little map, a symbol table, of where they are in memory. Then it does a second pass. This time, it goes line by line, translating each instruction into binary, and it uses that map it just built to fill in the correct addresses for all the labels. Pretty clever, right?
And really, that's the whole point of all this. Learning assembly isn't just some boring academic thing. It's about getting a deep, fundamental understanding of how software and hardware actually talk to each other. And that level of control, being that close to the metal, is exactly why assembly is still critical today for things that need every last drop of performance. We're talking game engines, operating systems, the firmware inside your phone, you name it.
So I want to leave you with a question to chew on. Now that you've peeked under the hood, knowing that every single thing you do on a computer, every click, every game, every app, eventually gets boiled down to these super simple instructions like add, load, and branch. How does that change the way you look at the software you use every day?
If this little tour helped you decode the language of hardware, do me a favor and hit that like button, share it with someone who might be interested, and definitely subscribe to Tech Talk 101 for more deep dives into the tech that makes our world tick. Thanks so much for watching.